Hello, this is the Chapter 9 video review of Material Science. This is the Callister text. So Chapter 9 was titled Phase Diagrams. So basically, a basic summary of this chapter is we're going to be using phase diagrams and looking at them. And phase diagrams are useful because we can use a phase diagram to show the number and types of phases present, and the composition of each phase, and the weight fraction of each phase. And we can find out all these stats just given the temperature and composition of the system. So let's just dive right into it. So for many systems, there's going to be at a specific temperature, there's going to be a solubility limit, and this is the maximum number of solute atoms that can dissolve into the solvent at that temperature. So we can calculate the solubility limit based on the phase diagram again. So as you can see on the phase diagram here, for sugar and water, we see that at a temperature of 20 degrees, we'll have a maximum solubility limit of 65 weight% sugar. And if you notice right here on the phase diagram, it'll be at this little point right here. So after that 65%, we can see that it turns into this phase, which is a liquid and solid sugar. So at that point, we'll have some solid precipitate in the liquid sugar and water. So just to highlight some of the important parts of these phase diagrams, on the left side, on this scale, we have the temperature, and on the bottom, we have the composition scale. So this should just be the weight% of the solute. So also, it's important to distinguish the difference between components and phases. So the components are the elements or compounds which are present in the alloy, and the phases are the physical and chemically distinct material regions that form, such as in this diagram, we have the lighter regions, which are the beta, the lighter phase, and the alpha, which is the darker phases here. So using the example from the previous slide, the components would be the sugar and the water, and the different phases would be the pure sugar and the liquid sugar and water, and then also the solute sugar in the water. So on this slide, we're talking about the effect of temperature and composition. So as you can see, since the left scale is temperature, the temperature does directly affect what phases are present at a certain composition in a system. So as you can see on this line right here, this blue line, this line will be the boundary between the two phases. So at any point when you're on the left side of the line, you'll have a liquid solution of just syrup, which is just water and sugar, and on the right side you'll have liquid sugar and you'll have solid sugar precipitate. So if you're at a higher temperature, like up here, we see that you can actually have more sugar dissolved inside the water. However, if you dip below that boundary line, we'll see that at the same composition of sugar, but a lower temperature, we'll have solid precipitate form. So changing slides, now we're talking about back to components. So to have the right solubility, we have to have the components that match up correctly. So in a simple system, we have nickel and copper here. And nickel and copper are soluble within each other. The rules for solubility is that both of them have to have the same crystal structure, and here we see that they both have the FCC, face-centered cubic structure, and we also have to have similar electronegativities, and lastly, we have to have similar atomic radii. So here, again, we can see that they have the same FCC structure, their electronegativity values are relatively close, and their radiuses, atomic radiuses are close too. So these will have complete solubility within each other. So on this slide, we can see a phase diagram of the copper-nickel system. And here we see that this is a binary system, meaning that there are just two components, the copper and the nickel, that make up this entire system. And again, we just want to indicate that the phases are all these phases are a function of temperature, of pressure, and of concentration. However, most of the times on these diagrams, since we can't show all three, so we only have two axes, the pressure is held at 1 atmosphere constant. And this is usually a standard that's held. So here again, as we saw on the first slide, this is just a phase diagram of the two components. And again, this just shows what phases are present at a certain temperature and a certain concentration of solute. So here in this system, we see that we have two phases, but we have three different phase fields. And that's because here up on the top in the green, we'll have a liquid phase only. And here in the bottom, we're going to have only a solid phase, so that's just going to be only solid solution. And right here in the middle, in the white, it's a special place, we have liquid and solid solution. So we'll have a combination of both of the phases. So the example we've been using this whole time is the copper-nickel system, and the copper-nickel system is an example of an isomorphous binary phase diagram. And what this means is, first of all, it's binary, meaning there are only two components, the copper and the nickel. And second, it's an isomorphous phase diagram, which means that they have complete solubility of one component in another. This means that, as you see on the bottom, the concentration percentage goes from 0 to 100. In many other systems, like the steel systems, we'll see that the weight percentage, usually on the bottom, only ranges from about 0 to 1%. And that's because if you put too much carbon in a steel system, you generally don't have much change after 1%. The excess just pulls up and precipitates. So now we know what phase diagrams are, let's talk a little about how to use phase diagrams. So rule number 1, if we know the temperature and the concentration, then we know which phases are present. And again, we can use this just like a regular old graph. We just go to the temperature on the left scale, and then we go right horizontally until we reach the weight percentage of the solute. And at that point, you can see, just like this B, if we started at 1250 C, which is right here, we would make a line out to 35 weight percent. And we'd see right there at B, we have two phases, which are the liquidus and the solidus state. And then based on what temperature and what solubility you're at, you can find out exactly what phases are present at any temperature and any solubility. Solubility percent. So rule number 2 of the phase diagrams is that if we know the temperature and the concentration, then we can determine the composition of each individual phase. So that means we'll be able to find how much percent carbon we have in the liquid phase and how much percent carbon we have in the solidus phase, or whatever phases are present at that temperature and concentration. So let's skip ahead. So let's go to point B. So at point B, we have a temperature of 1250 degrees C. So let's draw that out on the left. That's right here. And we have a weight percentage of nickel at 35 weight percent. So it's right here on the purple line. So if we do our general rule, go out from the temperature and go up from the composition, we'll see right here at B is what phases are present. So here we have the liquidus and the solidus present. So from this point, if we move directly horizontal to the left until we hit the green liquidus line, and then we come straight down from there, we'll land at 32% on the nickel. What this means is that we have, in the liquidus phase, we have 32 weight percent nickel. And then if we go straight again back from B to the right until we hit the blue solidus line, and then we go straight down from there, we'll hit 43 on the percentage scale. And this means that we have 43 weight percent nickel in the solidus phase. So from there, we can use the temperature and the concentration phase of the whole thing, of the whole system, to determine the individual compositions of each phase. That's really useful. So rule number 3 of phase diagrams, and this is kind of just building on rule number 2. So again, if we know temperature and concentration of the system, then we can determine with rule 3 the weight fraction of each phase. So basically, we can determine what percentage of the total weight is each phase. So we do this by using these formulas in the bottom left. So we'll look at the composition of the solidus. For the weight fraction of the liquidus phase, we'll use the composition of the solidus phase divided by the composition of the solidus phase and the liquidus phase. So if we look at the diagram, this gets a little bit easier. Alright, so starting at the same temperature and concentration as last time, we're going to go to point B. So that's right around here. So the weight percentage of the liquidus is going to be the composition of the solidus phase. And to find this, just like in rule 2, we're going to go from the composition and we're going to go right until we hit the solidus line. So, and then we're going to go down and find that that is 43%. But since we just want the blue portion of this, just the solidus portion, we're going to subtract off, going to subtract off the composition, which is the 35. So 43 minus 35, that's going to leave us with just the solidus portion. And then we're going to divide that by R plus S. So this is going to be S minus R. So we're going to go from the point B out to the solidus line, 43, and we're going to subtract off from point B to the left and hitting the liquidus line, so that's 32. So here, again, we'll see right in this box right here, we'll have 43 minus 35 over 43 minus 32. We come up with a weight percentage of 73%. So that's going to be the weight percentage of the liquidus phase. And either or, if you want to find the weight percentage of the solidus phase, since we know this is a binary system and only those two phases are present, we can either subtract this 0.73 from 1, or we can just do the same thing, but instead we're going to look at the R instead of the S on top. So either way, you're going to come up with 27% of the solidus phase of weight percent. So that last rule was a little tricky, and some people get a little confused about why for the liquidus phase do we put the solidus on the top, and most people would assume that you'd put the liquidus on top. But if we think of it as a lever, then it gets a little less unclear. So if you look at the tie line, which is just that purple line, which is at what concentration we're at, and then we look at the small line to the left, which is the liquidus line, the green, and the right is the blue line, which is the solidus line, and we translate that over here and look at it, think of it as a lever arm, then we can kind of see how the equation is derived a bit better. So here we'll see that the liquidus phase is just the mass of the liquidus over the mass of the liquidus plus the mass of the solidus, and that makes sense. And then if you relate it with this lever, we can easily see that the mass of the liquidus is actually just the solidus length over the the liquidus length over the solidus length and the liquidus length. And that's how we derived up that weight fraction equation. So this is a fun slide here that that helps us show how the microstructure really depends on temperature. So here we're going to look at this tie line, the purple line again, and it's going to be at 35 weight percent a nickel. So we're not going to change the weight percent, and all we're going to do is see how the microstructure varies with temperature. So up here at A, we're going to have a temperature of 1300 degrees Celsius. And here we see that there seems to be 0 particles. It seems to be all liquid, and there's absolutely no particulates in that. And then we move down a little bit of temperature. We hit B, and this is going to be roughly 1275 Celsius. And right here at that 1275 degrees Celsius roughly, we see that we hit that liquidus line right there. So right at that line we're going to see some particulates starting to form, and those are just the next phase coming into the diagram. And then we move down a little bit more, we move into the clear region, the clear white region, and this is 2 phases present, the liquidus and the solidus phase. And again here, as you can see right at this little diagram, so at this point we see that the particulates are getting bigger. And then again, if we move down to D, we'll hit the solidus line, and again in the diagram we can see the microstructure is changing even more. We're starting to see larger particulates. And again, if we move down clear into the solidus region, we'll see it's full solid. There is no more liquidus in there, and it's just single phase solid. So this whole chapter we've been looking at phase diagrams and how a different composition of the system can basically change what phases are present in the system. So why do we really care? So basically, what's the point? Why do we introduce these impurity atoms into a system anyways? Well, if we look at this, we can see that based on the amount of impurity composition that we put into a system, we can change the mechanical properties of the system and the material. So based on what we really want to use the material for, we would tailor the composition of the material differently. So like if we wanted to get maximum tensile strength, you can see here that we would put roughly 60 weight percent nickel in our nickel copper system, and that would maximize our tensile strength at about 425. However, it is important to note that if we look at the ductility graph, at around that same percentage, 60%, we also have a minimum on the ductility scale. The minimum percent elongation, that is. So we do have a trade-off here. If we want a high ductility, we wouldn't want to get around the 60% weight percent nickel, but if we wanted high tensile strength, we would. So it's important to look at these diagrams so we can know, based on what our needs are for a material, what percent impurity level we need. And that's about the gist of the first half of this chapter. And if you want to keep... And that about finishes this video on explanation of phase diagrams and weight percent compositions. So, thanks for watching. Have a good day.